Hello everyone, welcome to this video on Pyspark. Spark, as you may know, is an open source cluster computing framework written natively in Scala. However, the framework is available with wrappers in other languages such as Java and Python. In this series, we'll go through a lot of different aspects of Pyspark, including basics about how to set up your cluster, how to use cloud services with Pyspark, and some of the more advanced topics such as stream processing, machine learning, etc. Pyspark is a very vast topic and it's difficult to convey everything it entails into a single video. So at the end, I'll add a section about how you can further learn and enhance your Pyspark skills. Happy learning, and let's get started. Configuration of your Spark application is the most important step. It's the foundation of your entire Spark application. If you have not configured your application properly, you may end up with a very cool application which under or overutilizes the resources. Pyspark has two major classes for us to tweak the configurations according to what we need. These are Spark Context and Spark Conf classes. Some common properties we'll be working with are Spark's driver memory, executor memory, how many cores we want to use, how much data we are going to receive from our Spark application as output, and some simple ones like naming our application and tracking its progress. Obviously, we can't go through the entire list of configurations. You can find the entire list at spark.apache.org where the documentation is available. Now one might ask, what is driver memory? As you may know, Spark is an in-memory data processing framework, so it keeps the data in memory in the form of RDDs when it is applying some function on your data. The driver memory is the amount of data we get from the disk to the master to apply our functions on it. Driver also negotiates for all the resources your application needs from Yarn, as well as handle the main logic of your application and running it smoothly. Driver is relatively small. Executor is where the magic happens. The workers will be the ones in the end responsible for executing your job. The amount of memory your executor needs depends on what you are going to do. If you are just doing a simple map function where you just transform your data, you may not need that much memory. But if you are doing large aggregations with a lot of steps, you will need a lot of memory. It's worth noting that Spark needs 7% of extra overhead memory on each executor for everything to run smoothly. It's hard to explain all of these terms in just words, so why don't we jump into a very real scenario and try to figure out how we can configure our application in this scenario. Let's say you have spawned a 10-node cluster, 9 workers, 1 master on AWS, and now you want to run a simple application on it. In the 10-node cluster that we have, let's assume that we have 16 cores or virtual CPUs on each node and 64 gigabytes of RAM on each node. Now it's very hard to come up with a one-size-fits-all configuration which will work for all the applications. However, there are some bad practices that you can avoid. One of such bad practices is having fat executors. In this particular scenario, we had 10 nodes and one of them would be used as a driver and we'd be running one executor on each of the other node. As you can see, each executor is using all the memory and compute resources of that node. This is a bad idea for many reasons. One of them being that Spark applications usually read and write data from a distributed file system such as S3 or HDFS. Having such a configuration would lead to a lot of garbage collection and reduced parallelism while we write to these distributed file systems. On the other hand of the spectrum, we have something called as quote-unquote lean executors, which are just the opposite of what we just encountered. In this particular scenario, we would run a lot of executors within each of the node. Essentially, one executor per node. This is also a very bad idea, as if your application is using some common table or a common broadcast variables, it would be copied multiple times on each node, which would reduce the efficiency of your application. So what is the best configuration? Like we said earlier, there is no best configuration. There is no one-size-fits-all configuration that will work for any application. However, it's a good idea to have 5 cores per executors and then divide the memory accordingly. Cloud providers like AWS and Google Cloud provide a very good user experience for setting up your cluster in just a few clicks. Dynamic allocation is a new thing in Spark. It allows your driver to kill and spawn executors on the fly as required by your application. You still have to define boundary conditions of how many minimum and maximum executors you want and what should be the initial condition of your application. But since it's in beta stage, most developers shy away from it and still rely on user-defined configuration. If you are a Python developer like me, Pyspark may seem unnatural at first, as the backbone of Pyspark is written in Scala, which is a compiled language, whereas the wrapper is written in Python, which is an interpreted language. Zeppelin notebooks kind of bridge this gap, where developers are more comfortable with a Jupyter-like environment where they can run each line one after the other and see the output. They can now run Spark applications in a similar fashion where they can spawn the application on a cluster and then run their applications line by line to either debug or do a large-scale data analysis. Once you are ready with your configuration, you can see all the configuration values with a method called getAllConf and then create a Spark context finally out of it, which will then be used to open files and run your Spark application. Spark has come a long way from just being an improvement over the existing MapReduce algorithm. Not only does it have a very robust code maintained by thousands of developers worldwide, it also allows us to build applications based on more sophisticated techniques such as stream processing and machine learning. Now that we have learned how to configure our application, let's try and see what kind of applications we can run. This is a very simple application. We have a CSV file in S3 that we want to read and see how many lines it contains. First, let's use the primitive RDD based APIs and see how it performs. You would need an S3 key and secret code to actually access this bucket. But this is just related to how Pyspark connects with S3. If you are working with HDFS, you may not need these configurations. The data is just a dummy data set containing the name of the shop, the city, state, some sort of score, and the amount that was spent there. With simple RDD based APIs, there's a simple dot count method that you can call on the RDD to see how many lines there are in that dataset. You can see that with that file, it took about 3 seconds to tell us how many lines there were in that dataset. Now let's try performing the same task on the same file, but this time we'll use the more modern Spark DataFrame API to find how many lines there are in that file. Now as you can see, with the Spark DataFrame API, I now have to tell Spark how many columns there are in my file and what type should be there in each column. This allows Spark to optimize under the hood while getting the data from S3 to my cluster for processing. A similar dot count method is available in DataFrames API as well to count how many lines are there in the file. Now as you can see, the task only took 0.7 seconds as compared to the 3 seconds with the RDD API. Why are DataFrames performing better than our old RDD based APIs? So the reason is because CPU improvements have kind of tapered off in the last decade, whereas storage technology is still improving almost 10 times every 5 or 6 years. So when we read data from S3 and Spark is able to compress it better due to us telling it what kind of data to expect, it is able to perform queries much faster as compared to RDDs, which just assumes that everything is a string. Now let's try and compare some complex queries and their performance on both RDD and DataFrame. First, let's just try and find out what was the total sale or total amount for the file using the RDD based API. First, we would have to apply a .map function to get the last column, which can be referenced by -1 object in Python, and then call a .sum method, which is again an RDD based API, to get the total sum of that column. For DataFrame based APIs, we have a .ag method, which then can be used with a sum method to get the total amount of the column amount. As you can see, DataFrame APIs again outperform the RDD based APIs. Another complex query that we can run, in this case group by, is to see what was the sale per state. Now this would require first a group by operation and then an aggregate operation within each group. With RDD based APIs, obviously we'll have to run a .map method first to get the columns that we need, then a .group by method to group the data for each state, and then a sum method which will then give us the total sum for each state. With DataFrame based API, there is a .group by method directly available that can be applied on any column, and the similar ag method that we used in the previous cell. As you can see here, again the DataFrame based APIs outperform the RDD based APIs. Finally, let's run one more task, which is to find the distinct number of shops that we have in our file. This distinct operation under the hood uses a reduce by key method in both RDD and DataFrame based APIs. However, DataFrame based APIs again outperform RDDs as their data footprint is much smaller. Compared to RDDs, datasets use much less memory, almost 75% less memory, especially when caching. This is because of the efficient serialization and deserialization protocols that are used by datasets, since they know the type of each column, so they know what kind of data to expect. Datasets APIs has a lot of benefits like we mentioned earlier. They are more compact, they reduce the memory footprint. Now Spark knows what kind of data it is expecting in each column, so it can optimize based on that. The earlier improvements in Pyspark or Spark were based on how Pyspark or Spark was efficiently able to serialize and deserialize the data. However, developers soon realized that it's not the serialization and deserialization, but rather the file format itself is what is holding Spark back from performing to its full potential. So, Spark developers came up with the idea of columnar format, commonly known as Parquet format, where instead of storing data line by line, they now store data column by column. This has obvious advantages, like if you want to perform a task only on a specific column, Spark can fetch just that column instead of going line by line and picking the column from each line. One more advantage of Parquet is that it stores metadata along with the data, so we don't have to provide Spark with the types of each column. Let's try and run some similar queries that we ran on RDDs and DataFrames, now with the DataFrames based on the Parquet data format. You can see that RDDs are again outperformed by Parquet formats since group by operations are much faster on columnar based files. Now let's talk about some of the more advanced topics like Spark streaming. Big data, as you know, never stops. Most of the modern day applications never stop spitting out data, whether it's your telemetry data, your location data, it never stops. Spark streaming APIs allow us to build application which can handle a steady flow of data and process the data as and when it's captured in the system. The APIs, as usual, are very simple to use. Just like with our RDDs and our DataFrame based APIs, we just create a Spark context. But along with that, we also create a Spark streaming context along with a time frame band, which is set here as 5 seconds, as you can see on the screen, which tells Spark that every 5 seconds it has to batch the transactions and then process them. And then we'd also have to specify an input folder in which all of the incoming streams are getting written to. This can be a local folder, or it can be an HDFS folder or an S3 location. Again, based on our RDD APIs, we'll perform some simple transformations like splitting the string and getting the columns that we need. And then let's see what our data actually is. So you can see for each batch, it's giving me the transactions, which is nothing but the state and the amount, as we have captured only those columns. And at every 5 seconds, it will refresh and give us the transaction that happened in that batch. Now, let's go a step further and try and perform some more complex operations on this particular stream of data. Earlier, we were just printing data as each batch in the stream came through. Now let's try and checkpoint our streams as well. We'd again initialize Spark context and Spark streaming context as usual. We read our data from the same directory as we were, perform some simple transformations using the .map method, but now we'll add a checkpoint folder as well, which will contain the aggregates of whatever has been seen in the stream so far. Right now what we are trying to do is we are trying to find what is the amount per state that we have seen in our file. We write a simple update function which will initialize the running count as 0, and if the count has already been initialized, it will add the new value it is seen in the stream to it. In this cell, we are just applying a .map transformation again to get the state and amount column from our file. Again, we can update the state key using this update state by key method. And finally, we'll write our data into a new file which can then be served as an input file to either another Spark application or a dashboard that we are going to see right now. As you can see, the dashboard updates on the fly as and when new data is passed on to the Spark application through the stream, and the aggregates for each states are updated on this dashboard. You can see that this can have a large amount of applications. The data could be coming through an IoT device and then be displayed on a dashboard, or it can be consumed by some other Spark application as well.